Yeah, that was fun. All right, guys. So today we're going to talk about intervals of increase and decrease. It's going to be a pretty easy day, but before we get going on that, I want to just review the mean value theorem. What I want you guys to do for your do now is find the value of C that's guaranteed to exist by the mean value theorem for this function f of x equals ln of x on the interval from 1 to e. And just to, for anyone that wasn't here, what's the first step you guys should take? What is the first thing you have to do? Find the slope of the secant. Now you have to do your f of b minus f of a over b minus a. Then what's the next thing you got to do? Find the derivative. Nice. And then what do? Set them equal. And then what? Hey, you solve that. And as long as the solution is greater than 1 and less than e, you call that solution C. So the first thing that you're going to have to do is get the slope of the secant. Oh, I checked you with. All right, kids. Anyone get an answer? Tim, you're raising your hand. You got something? What do you got? All right, Tim got x equals e minus 1. Did anyone else get that? Ooh, Ellie did jammed it. That's some good backup. Wow, this is good. Yeah, it is x or c equals e minus 1. Let's talk about it, shall we? That was good, guys. I thought you had that. I thought you guys were just talking about other stuff. Okay. Yep. Thank you for checking me because after break I could forget. All right. So with the mean value theorem, the first thing you want to do is find the slope of the secant. I have the ln of x drawn here, and we want to find the slope from where x is 1 to where x is e. So you had to get the y coordinates. Now you guys know what the ln of e is? 1. All right, because it's the log base of your d. It's the exponent you raise e to get e. So that's 1 minus the ln of 1. The ln of 1 is 0 over the change in x's. All right, e minus 1. So the slope of the secant is 1 over e minus 1. And the mean value theorem guarantees that for at least one value of x between 1 and e, the slope of the tangent will equal the slope of the secant. So you get the derivative, which is 1 over x, right? The derivative of ln of x is 1 over x, and you set them equal to each other. So if you have 1 over x equals 1 over e minus 1, x equals e minus 1. You could have cross multiplied, but that would have just been silly. Okay? And then you have to ask yourself, okay, is e minus 1 in between 1 and e? Can someone give me an idea of what e minus 1 equals? 1.7-ish. You're on today. Switch over. This is your day. Yeah, and so that's definitely between 1 and like 2.7-ish. So, yeah, so you call that value C. That's where the instantaneous rate of change equals the average rate of change. See it? No? Audrey, question? What's bugging you? Well, do you see the first thing though? First, you had to get the f of b minus f of a over b minus a. You had to get the slope of the secant line, just slope formula. So you know they gave you the a and the b, the endpoints of your interval. That's your a and your b. So you have to get the y's that go with each of those. That's what the numerator is. Difference of the y's over difference in the x's, and you just set that equal to the derivative and solve it. And as long as that solution, the derivative ln of x, okay, which is 1 over x. And you set them equal, and as long as your solution is in between the endpoints, that's your value C. There's something about this bugging me, but I don't know where it is. You want to ask, or just want to? Okay. Okay. If you think of it later, ask me. Yes, yes. Well, the mean value theorem just guarantees that the slope of the tangent line, the derivative, will equal the slope of the secant line. You're saying what's the difference between the mean value theorem and the derivative, you were asking? The mean value theorem says that the slope of the tangent, which is the derivative, will equal the slope of the secant, which is the change of y's over change of x's. Okay, so yeah, you are going to get the derivative to find where the slope of the tangent equals the slope of the secant. You set them equal. Yeah, and whatever that solution is, as long as it's between A and B, that's your C. That's guaranteed. So let's see how well you did on the homework. It's a little small, so I'll try to back out. So on the first page, the multiple choice, 1 is C, 2 is C, and 3 is A. And then on the other side, I know the wording for 4, you not only had to write the equation of the tangent line, but find out where it crossed the y-axis. That was a little rough. The answer for that was C. It was 0.31. And then in 5, they just gave you this chart, and they asked you, how do you know that h of r has to equal some value? And then they said, how do you know h prime of r has to equal some value? And we can go over that one if you'd like. Part B was the mean value theorem. Part B, if you got h of 3 minus h of 1 over 3 minus 1, you did get negative 5. So you know that the derivative has to equal negative 5 for some value of c between 1 and 3. So for part B was what we were talking about now, but part A went back to the intermediate value theorem. We can look at that in a minute. How did you do on the first side? Yeah? So do you want to go over 4 and 5? What do you want to go over? 4 and 5? Okay. Is anyone still copying anything? Or is that great? Okay, is this what I want? Yeah, I guess this is it. Okay. So for number 4, they gave you this chart. I didn't copy the whole thing, but basically in the chart they gave you values of x. They gave you f of x values, so the y coordinates of the points. And then the third row were the derivatives of those points. And they ask you to find out where the tangent line that has the same slope as the secant line would cross the y-axis. So it was a lot to do. So the first thing you had to do was, well, if the tangent line has the same slope as the secant line, I better get the slope of the secant line. So you had to, with the first point and the last point, get the slope. So you want to do the change in y's over the change in x's. I used the 10 first. So f of 10 minus f of negative 2 over 10 minus negative 2. So the first thing I do here is I'm getting the slope of the secant. And if you look up f of 10, it's 2. And f of negative 2 is 26. So I have 2 minus 26 over the change of x's, which is 12. So the slope of the secant is negative 2. You guys see where that's coming from? Okay, so that's the first thing. Now they said you got to find out where the tangent line that's parallel to that secant line crosses the y-axis. Well, if the tangent line is parallel to the secant line, it has to have the same slope. So you look at your whole chart of values, and you got to find the point where the derivative is also negative 2. And you see that that point is the point 423. That's where the derivative, the slope of the tangent, is the same. Okay. So now we want to find out where the tangent line drawn at this point crosses the y-axis. So the first thing you're going to have to do is write the equation of the tangent line. So to write the equation of the tangent line, we'll use point slope. So it's y minus the 23, right? Equals, what do we put in for the slope? Negative 2, and then parentheses, x minus 4. So over here I wrote down, so this would be the tangent line that's parallel to the secant line. Now we're almost there, kids. So you have the equation of the tangent line. If you want to know where any graph crosses the y-axis. Okay, you want to get the y-intercept of any graph. What do you know about that point where it crosses? What's the one thing you know if it's on the y-axis? The x-coordinate is 0. So to get where the y-intercept of any graph, you put in 0 for x. You set x equal to 0 and solve for y. And if you put 0 in for x, you multiply, you add, you get the y-coordinate there is 31. So the answer was 0, 31. It's kind of a lot for a little question, but hey, it's kind of enjoyable. Everyone get it? Just wondering now. Okay, let's try number 5. No more questions on this one? We get this? Now 5, the first thing they say is show why, they gave you the definition of h of x. H of x was f of g of x or something, okay? And they ask you about this interval from 1 to 3. I say, okay, and they gave you a chart of values. They're saying, explain why h of, I think they use r, would have to equal -5. Well, what you want to do is find the value of h at each of the endpoints. Like if you plug in 1 into h, it'd be f of g of 1 minus 6. And that all turns out to be 3. So in other words, this function h, when r or x is 1, the y-coordinate would be 3. And then you figure out, how about at the other endpoint of 3? You plug 3 into the definition of h, and it works out to be -7. So now you know on your graph of h, you've got this point, 3, -7. And they're saying, okay, well, if this is h was a composition of f and g. They were both continuous functions, differentiable. They're saying, okay, so why would that mean that h of r would have to equal -5? Is it true that h of r would have to equal -5 for some r that's in between 1 and 3? Well, if you look at this graph, I think it helps. If h is a continuous function, wouldn't it have to go through -5? Do you see that? Because it's up here at 3, and it's going down to -7. So you might not know where, but this is called the intermediate value theorem. Whenever you have a continuous function, it can't skip over any y values. So they could have made up any number. As long as it was between 3 and -7, it would have to go through it. So yeah, and all you have to say is, by the IVT, the intermediate value theorem, h of r has to equal -5 for some value between r 1 and 3. You can't get from up here to down here without going through -5. It takes on all y values. So that one I could see being like, what? But the second part is on the topic that we're talking about, in the value theorem. They're saying, now explain why h prime of r would have to equal -5. And I think they use c this time in part B. There's some value c between 1 and 3. Well, with continuous differentiable functions, we know that the derivative has to equal the slope of the secant. So this time we want to get the slope of the secant. So if we take h of 3 minus h of 1 over 3 minus 1, we would get -7 minus 3 over 2. Oh, look what it equals. -7 minus 3 over 2. -5, right? What we just found was that the slope of the secant, the slope of the line going from here to here, the straight line, that slope is equal to -5. And the mean value theorem guarantees there's some point, even though we don't know what the graph of h looks like, we know there's some value c between 1 and 3 where the derivative, the slope of the tangent, equals -5. So this time we would just have to say, by the mean value theorem, h prime of c has to equal -5 for some value of c between 3 and 1. So the function h has to equal -5 because of the intermediate value theorem. It's got to go through there. But the slope, the derivative, has to equal -5 because of the mean value theorem. Alrighty? All right, you ready for some easy stuff? Oh, yeah. Well, the mean value theorem is actually important because it's what's used to show that when a function's increasing, the derivative is positive. And when a function is decreasing, the derivative is negative. And there's a little proof written here, but that's exactly what it's saying. And this is huge. So you don't have to look at a graph to know when a function is increasing or decreasing. You can just determine whether the derivative is positive or negative. And we know how to do that, right? So the big conclusion out of this is that whenever a function's decreasing, and it doesn't matter if it's concave up, if it's linear, if it's concave down, if it's decreasing, what do we know about its derivative? It's going to have to be negative, right? The slope of tangent is going to be negative. And if a function's increasing, whether it's concave up, linear, concave down, what do we know about the slope of the tangent? Positive. So if you're asked on what intervals is a function increasing or decreasing, you guys got to remember to think first derivative. You're going to make a sign chart for the first derivative. Remember sign charts? You're good at that. Yeah, you're good. The key with sign charts is to realize that any function can only change sign in two ways. Either when it's 0, right? You can just go from positive to negative. Or it can go from positive to negative or vice versa where it's undefined. So anytime you want to determine or make a sign chart for any function, including a derivative, find out where that function is 0 or undefined. Mark those off on a little number line, we call that a sign chart, and take test values. Okay? So if you do that with the first derivative, you find out where the first derivative is 0 undefined, you mark off those critical values, take test values, you'll know where the first derivative is positive and where it's negative. So you'll be able to answer the question, where is your function increasing and where is it decreasing? You like it? Yeah. You have, right? That's why the motion unit, although painful, was really, really helpful because it helped you kind of get a little taste of some topics to come. All right, so the first one, without actually graphing this, we want to know where it's increasing or decreasing. So that's all about the first derivative. So tell me what the first derivative is. 24x minus 6. Okay. Now we said that a function can only, critical values, change sign where the derivative is undefined, so it does not exist, or where the derivative equals 0. Are there any values of x for which this derivative is undefined? No. Okay, and some people get confused by that. If it's not a fraction, it's going to be defined, okay? It's just that there's a number that if you plug it in, it makes the denominator 0. That then it won't be defined there. But there are no values. I'm going to draw a little empty set. So the only way that this first derivative could change sign is if it's 0. So set it equal to 0, and tell me what you get for x. First derivative is x equals, I'm sorry, what'd you say? 1/4. Did anyone else get that? Yeah? Okay, good. 6/24. So if this first derivative is going to change sign, it's going to happen at 1/4. So when you make your sign chart for the first derivative, the only number you should put on there is 1/4, because that's your only critical value. That's the only place it could change sign. Put it right there. It doesn't matter where. Anywhere you want. Yep. There's no right answer for that. All right, now, give me a number greater than 1/4. 9. All right, we'll give her this one, all right, because she was so little, and I'm like, you know. Okay, so And it doesn't matter whether you use 1 or 9 or any number. As long when you plug that into the derivative, we're all going to get the same answer. You want to take 1,000, plug it in. Is the first derivative positive or negative? Positive, right? 24 times 9 minus 6. We don't care what it is. It's positive. Now take a number less than a fourth. No, I'm not going with you because. All right. I thought you'd say 0. All right. All right, Ryan. Let's just go with 0. I don't know how these people like to work. All right. 0 is a number less than a fourth. So, but it doesn't matter which one you pick. As long as it's less than a fourth, the derivative will be. I always like to chat when I go to the phone. Okay. We now know exactly where the first derivative is positive and where it's negative. We're ready to answer the question. Where is the function decreasing? On what interval? That's nice, but in this country we read left to right. Yeah, that's right. Okay, so? I know, that was just bad. I know. Negative infinity, 1/4. Yeah, if you ever write an interval notation, always take a look. If the number on the left isn't less than the number on the right, you did something wrong. You wrote it backwards. Yeah. It's not backwards, there's no such thing. Okay, now where is the function increasing? You're whispering into the mic, saying bad things. Yeah, so from 1/4 to positive infinity, we know that this function, even though we can't see it, we know it's going to be increasing there. I'll just scroll up so you can actually see that. Got it? Yeah. If you know the sign of the first derivative, you know exactly where your function is increasing, where it's decreasing. Okay, now that I did a nice easy one, why don't you do example B on your own? No, you know what? That's a test. It's like a mathematical test. It's not a classroom test. All right, the kids have been working on example B. All right, so let's just see where you went wrong, shall we? If you did go wrong. So when you got the derivative, you should have 12x cubed minus 24 squared plus 12x. All good? So it always exists, so the only critical values will be where it equals 0. So to see where it equals 0, you should have factored out the 12x first. Saying, did that. Good. Then this x squared minus 2x plus 1 can be factored again. That's x minus 1 times x minus 1. So your derivative, I know it's kind of small here, is 12x times x minus 1 squared. Now that's really nice. Do you guys remember in pre-calc when you would have a polynomial and you would factor it all, and you had a factor that was to an even exponent? You said it had even multiplicity. What happened with those polynomials at that root? They bounce. They didn't cross. So they would go to the x-axis and they bounce off. So did they change sign there? No. That's always going to be a clue. When you get your derivative and you factor it, if that factors to an even exponent, expect no sign change at that 0. Of course I did it on purpose. Because some kids, there are kids in this world, believe it or not, they'll check one value and they'll just assume it alternates. Okay, yeah, I know. I'm going to be above the other kids. I don't want to plug in a test value for every interval. I'll just do one. So yeah, so now when it comes to plugging in test values, plug it into the factored form. The great thing about this derivative is, you know, anything minus 1 squared, other than 0, is going to be positive. So when you want to see when is this derivative positive or negative, basically all you care about is the factor x. The other factor, 12, is always positive, and x minus 1 squared is always positive. You're not going to get 0 because those are our critical values. So really, if x is positive, the derivative will be positive, and if x is negative, the derivative will be negative. All right? So you can take your test values like 2, but it'll be positive, positive, positive. Take a number like a half. All the factors will be positive. The only way you're going to get a negative value for your first derivative is if x itself is negative. So that's the sign chart. And once you have the sign chart, now you can go ahead and state where your function's decreasing. So it should be from negative infinity to 0. and then increasing from 0 to 1, and then from 1 to infinity. At 1, the slope is 0. It's called a stationary point. It's not going up or down. So if you want to just include it, you can. Is that what you're going to ask? X not equal to 1, where it's increasing? But then what about like -7? Oh, and then you wrote next to it where X is not equal? Oh, that's right. Yeah, I get it. Okay. Questions about that one? All right, these are fun. The first two examples, though, we went to get critical values, and we said, oh, the derivative always exists, so we just set the derivative equal to 0. I wanted you to see what happens when the derivative involves a fraction. Yes. Yep, kids are excited about this one. Yep, the kids are so psyched. All right, settle down, kids. All right, kids, tell me what the derivative of the first term is. What is 3x to 2/3? Yes, Cameron. No, Cameron. Oh, we did the whole thing. Good. 2x to the -1/3 minus 1. Do we agree with that? You see it? Now, here's the thing, guys. This derivative involves fractions. I don't see any fractions. Well, it's 2 over. Yep, it's a 2 over the cube root of x minus 1. When you have a derivative that involves fractions and you want to make a sign chart, you're going to have to combine those into a single term. And to combine fractions, what do you need? Common denominator. Your elementary school teachers did a good job with you. So what's the common denominator going to be? The cube root of x. So this first term is fine, but I want the second term to be over the cube root of x. Yeah, what you do is you multiply by the cube root of x over the cube root of x, right? So, yeah, it's 1. I mean, you probably didn't have to do that for this one. It is a little silly. I want you to see it. Well, the thing is, now they have a common denominator, you can combine them. So our derivative is equal to 2 minus the cube root of x over the cube root of x. What's that? Yes, you are. When does a fraction equal 0? A fraction equals, give me an example of a fraction that equals 0. No, that does not equal 0. If you have 0 halves, that's 0. Give me another fraction that equals 0. Nope. 0 thirds is equal to 0. If the numerator is 0, the fraction equals 0. But then it doesn't exist. Yeah. So we have to, critical values come from both of these situations. So to find out where the derivative doesn't exist, you set the denominator equal to 0. But critical values, we need to know both of these. To see where derivative equals 0, that's just when the numerator is equal to 0. I hate this little round thing all the time. It's in my way. Okay. I can't. It's right there. Okay. So let's look at where the derivative doesn't exist, when the denominator equals 0. How are we going to solve that? Cube root of x equals 0. There, you can cube both sides, you get x equals 0. That's a critical value. How are we going to solve the other equation when we set the numerator equal to 0? There it is. Now what? I like that idea. Well, let's add the cube root of x. So we have 2 equals the cube root of x. Raise each side to the reciprocal of the exponent, right? Because right now it's to the third, so you could cube both sides. Does that make sense? We would cube both sides. So we're just going to cube both sides. So I'm going to switch sides because I like the x on the left. So x equals 8. Oh, shoot, we're going to run out of time. We have 2 critical values. So for a little sign chart, we're going to break it up at 0 and 8. Now, guys, when you're taking test values, make them perfect cubes. Can you give me a perfect cube that's greater than 8? What? 27? Excellent. Okay. Cube root of 27, that's 3. That's positive. How about the numerator? Negative. Negative over positive is negative. Give me a perfect cube between 0 and 8. 1. I love it. Cube root of 1 is 1, so the denominator is positive. What about the numerator? Right, because 2 minus 1 is positive. All right. Give me a perfect cube that's negative. Okay. That's not a perfect cube. Negative 8? Okay. Cube root of negative 8 is negative 2, so the denominator is negative. 2 minus negative 2, that's positive 4. So positive over negative, negative. So with that, I'm cheating here. Oh, I thought I had it. So your function is decreasing from negative infinity to 0. Yeah, but then some kids might not know. And then from 8 to positive infinity. Oh. And f is increasing from 0. Oh, I was going to write, whoa, that's 0 to 8.
Oh my God.
That was wonderful. I'm going to fill in the summary for the kids at home. All right, nobody backwards tomorrow. So function increases where the derivative is positive. A function decreases where the derivative is negative. Which numbers are used to label a sign chart? Critical values. And why do we only use critical values to label sign charts? Because a function can only change sign. Bye, guys. A function can only change sign at a critical value. Okay. And that is the end.